Okay, do me a quick favor. Just think about picking up your coffee cup. Seems simple, right? But what if I told you that underneath that one tiny action is an incredible biological puzzle that your brain solves in a literal flash? Today, we're going to unravel that very puzzle.
I mean, think about the real problem here. How does your brain pick one precise movement out of a sea of a million other things it could do? And, maybe even more amazing, how does it tell the entire rest of your body to just stay put? You see, this isn't just about telling a muscle go. It's a really deep problem of selection and suppression. To get this, you have to think about muscles as working in pairs. So, to do anything, like flexing your bicep, that muscle is the agonist, the mover. It has to be activated. But at the exact same instant, its opposing muscle, the tricep, the antagonist, has to be told to relax, to be inhibited. Every single move you make is this perfect, simultaneous balancing act of go for some muscles and stop for others. Now, this system it's just a masterpiece of biological engineering, right? A delicate dance of activating and inhibiting. So that brings up a really important question. What happens when this incredibly delicate system of choosing and suppressing just breaks down? While when it fails, you can get conditions like akinesia. And this is a profound difficulty in initiating a movement. It's not about being weak, it's about not being able to start. It is a key and truly heartbreaking symptom of Parkinson's disease. And it perfectly shows us what happens when the brain's go signal just can't seem to get through. And that's the mystery we're going to solve. The masterminds behind this whole operation are a group of structures nestled deep inside your brain. We call them the basal ganglia. And you can think of them as the brain's ultimate gatekeeper for movement. Okay, so let's meet the key players here. First up, you've got the striatum. The easiest way to think of it is as the main input hub, kind of like a receiving dock. When the thinking part of your brain, the cortex, decides, hey, I want to move, the signal lands here first. Next up, we have the output structures, the globus pallidus and the substantia nigra. And here is where it gets really fascinating. Their default setting is on. They are constantly firing, constantly putting the brakes on movement by inhibiting another area called the thalamus. So, by default, the gate to all movement is held firmly shut. Now for the magic ingredient, the thing that unlocks this whole system, the substantia nigra pars compacta. It's a tiny little area with a massive job. It produces the absolutely critical neuromodulator, dopamine. And as you're about to see, dopamine is basically the key that turns in the gate.
And the last major player we need to know is the subthalamic nucleus. Its role will make more sense in a minute, but for now, just think of it as a powerful booster for the stop signal. It's all about helping keep that gate closed.
All right, we've met the whole crew. Now let's see how they actually work together. The logic of the basal ganglia is built on two competing circuits that are running in parallel. You've got a go pathway and a stop pathway. It's really this beautiful push-pull system. The direct pathway, that's all about promoting the movement you want to make. It's like hitting the gas. But at the same exact time, the indirect pathway is working to suppress all the other movements you don't want to make. That's like pumping the brakes. And whether you move or not all comes down to which pathway wins out. So let's trace that go pathway. Step 1, your cortex sends an excite signal to the striatum. Step 2, the striatum sends a stop signal to the GPI. Now hold on, remember the GPI's job is to constantly put the brakes on the thalamus? Well, by inhibiting the GPI, you're literally telling the brake to stop braking. It's this brilliant double negative called disinhibition. And with that brake off, the thalamus is free to excite the cortex and bam! That's what allows movement.
Okay, now for the stop pathway, it's a little more roundabout, but its purpose is simple, to slam on the brakes even harder. It uses a slightly different route with a couple of extra steps, but here's the bottom line. This pathway ends up supercharging the GPI. It tells the main brake to press down with extra force, powerfully shutting down the thalamus and stopping unwanted movements in their tracks.
So, this is the crucial takeaway. The default state of your motor system, thanks to the basal ganglia, is to be still. The whole system is designed to be inhibited. So a voluntary movement isn't about pushing some go button. It's a beautifully precise and coordinated release of the brakes on only the specific movement you want to make.
This is all amazing, but how does the brain actually choose? How does it balance the accelerator and the brake from moment to moment? Well, the answer is that master regulator we talked about earlier, dopamine, which comes from the substantia nigra.
And the absolute genius of the system is how dopamine does this. It actually hits two different kinds of receptors. On the go pathway, it hits D1 receptors, which is like boosting the accelerator. At the exact same time, on the stop pathway, it hits D2 receptors, which is like muffling the brakes. So one chemical, dopamine, perfectly tilts the scales. It cranks up the go and turns down the stop, giving you smooth, intentional action.
So now, with this incredible model in our heads, let's go all the way back to our opening mystery. We can finally understand what's really happening in Parkinson's disease when this elegant gatekeeper system starts to fail.
The problem in Parkinson's disease is tragically specific. The brain starts to lose those precious dopamine-making neurons in the substantia nigra pars compacta. The source of that master regulator signal, it just starts to fade away. And without dopamine to tilt the scales, the balance is just catastrophically thrown off. The go pathway gets weaker and becomes less active. At the same time, the stop pathway goes into overdrive and becomes overactive. The result is simple and devastating. The brake is slammed on, but the accelerator is weak. The gate is effectively locked against movement.
And this model just perfectly explains the classic motor symptoms of Parkinson's. That slowness of movement, bradykinesia, that's the weakened go signal. That difficulty starting a movement, the akinesia, that's the overpowering stop signal. The rigidity, that comes from the constant braking, and even the tremor is thought to be the result of these circuits just being totally out of balance.
But you know, the story doesn't actually end there. The basal ganglia's amazing system of selecting one thing and suppressing everything else, well, it's not just for controlling our muscles. It turns out to be a fundamental principle the brain uses for a whole lot more.
So that begs a really fascinating question. Is this whole go-stop system, this gatekeeper model, is it only for physical actions, or could it apply to our inner world too?
And the answer is, yeah, it's absolutely fundamental to our mental lives. These exact same circuits are involved in forming our habits, in processing reward and motivation. They even help to gate the flow of our thoughts and ideas. They're the gatekeeper not just for what we do, but also for what we think, and even how we feel.
And that leaves us with a final, kind of mind-bending thought. If the basal ganglia help form your habits, choose your thoughts, and guide your actions by constantly opening and closing this intricate gate, just how much of your daily life, from something as simple as brushing your teeth to your most complex decisions, is being quietly shaped by this silent gatekeeper deep inside your brain?